Alright, so for this problem, we must find a countable. I'll use this to abbreviate countable. Set C such that the sigma field generated by C is how do I make a cursive R? So, there it is. Yeah. Is the Borel sigma algebra on D, on the Borel sigma algebra on RD, which is the sigma. I don't know. I keep switching between sigma field and sigma algebra. They're the same thing, so I guess it doesn't matter. I sort of wish that the author would stick to one of them, but they don't, so I won't. And also, yeah, I don't know why. Anyways, so this is the sigma field generated by U, where U is the set of open subsets of RD. And of course, when I say open subsets, I mean open with respect to the standard topology. Okay, so let's try this set. Let C be the collection of all balls of radius r around x, where r is greater than 0, and x, of course, is x1 through xd, because it's an element of RD. However, r, well, actually, this is an element of QD, and R is also an element of Q. So basically, the radius is a rational number, and all coordinates of x are rational numbers. And by the way, this exercise is actually ends up being very similar to, let's see, I wrote it down here. Fall in Chapter 4, Exercise 5, which is that every separable metric space is second countable. Metric space means that there's a distance function. Separable means it contains a countable dense subset. And second countable means that it's generated by a countable set. And it's the same idea here as there. You consider balls of rational radius centered at points in your countable dense subset. And here, QD is our countable dense subset, because QD is dense in RD, and yeah. Okay, so each element of C is determined by a radius, which is a rational number, and the coordinates of x, which are all rational numbers. And so all of the things that can be used to identify an element of C come from countable sets, and there's only finitely many things, and so that means that C is a countable set. And furthermore, since each element of C is an element of U, which is obviously contained in the sigma field generated by U, we have the sigma field generated by C is contained in the sigma field generated by U. Because, of course, the sigma field generated by U, or we know that the sigma field generated by U contains C, and so the sigma field generated by C is the intersection of all sigma fields which contain C, and the sigma field generated by U is one of those sigma fields, and so therefore the sigma field generated by C is contained in the sigma field generated by U. So we want equality here because the sigma field generated by U is the Borel sigma algebra. So to get equality, we need to prove that the sigma field generated by U is contained in the sigma field generated by C. So next, let U be an element of U. I claim that U is contained in the sigma field generated by C. And then this becomes a lot like the last exercise. So if U is contained in the sigma field generated by C, and this holds for every single U in the set U, then the sigma field generated by U is a subset of the sigma field generated by C. And that's what we're looking for. Okay, so to prove this, let X be an element of U. Since U is generated by open balls. X is in BRX, which is contained in U. This holds for some R greater than 0 and X in RD. Oh, I guess I should have said this. When I say BRX, this is the ball of radius R centered at X. So BRX consists of all points Y such that the distance between X and Y is strictly less than R. Okay. Alright, so anyways, with that out of the way, let's continue. Choose S, which is between 0 and R, but also a rational number. Okay. Since QD is dense in RD, there exists some element Y which is in QD, but also in the ball of radius S over 4 centered at X. And the reason we're using S and over 4 will become apparent. Okay. So then X is an element of the ball of radius S over 2 centered at Y. And that's simply because the distance between X and Y, by the choice of Y, the distance between X and Y is less than S over 4, and so in particular it's less than S over 2. So therefore X is in the ball of radius S over 2 centered at Y. And Y is an element of QD and S over 2 is a rational number, and so this is an element of C. And what else? The ball of radius S over 2 centered at Y is contained in the ball of radius R centered at X, because for all elements, say Z, in the ball of radius S over 2 centered at Y, what is the distance between X and Z? Well, it's by the triangle inequality less than the distance between X and Y plus the distance between Y and Z. And let's see here. So the distance between X and Y, well, that's going to be less than S over 2. And the distance between Y and Z, well, Z is in the ball of radius S over 2 centered at Y, so this is going to be less than S over 2. And so then this is going to be equal to S, which is strictly less than R, by the choice of S. So, come on. There we go. Okay, so for every element in the ball of radius S over 2 over Y, its distance from X is less than R, and so the ball of radius S over 2 centered at Y is contained in the ball of radius R centered at X. Okay. So what does this tell us? This means that there exists some set Vx in C such that X is contained in Vx and Vx is contained in U. And of course, in this particular case, Vx happens to be the ball of radius S over 2 centered at Y. Okay, so anyways, this is all we need. For every X in U, there is a Vx in C such that X is an element of Vx and Vx is contained in U. Okay, so now to finish this up, let V be the union over all X in U of Vx. Since each Vx is in C, and C is countable, V is a countable union of elements in C, and so V is in fact an element of the sigma field generated by C. Now each Vx is contained in U, so V must be contained in U. X is contained in Vx, which is a subset of U, which is a subset of V, for all x in U, so U is contained in V. Thus, U equals V, which is contained in the sigma field generated by C, and so U is an element of the sigma field generated by C. That's what we wanted. This holds for all U in U, and so U is contained in the sigma field generated by C. So sigma field generated by U is therefore contained in the sigma field generated by C. And hence, because this is the other direction of inclusion that we needed, we have the sigma field generated by C is equal to the sigma field generated by U, which is, by definition, the Borel sigma field on RD. And that's what we wanted to prove, and so we're done. And yeah, this exercise does look a lot like Fallen Chapter 4, Exercise 5, and there's sort of a picture that I drew in that excerpt when I did that exercise in my other playlist that you can go check out. And I actually drew a picture there to see, like, where did I come up with these strange, like, balls of different radii? And there's sort of a picture that you can use to figure out how to get these different sets. And I would have included that here, but I already included that in that video, so I would just recommend that you go and check that out if you want it. If you're more of a visual learner like I am, then that could be really beneficial. I also think it's really neat anytime you can do like a visual argument, because as soon as you see that picture, you can sort of immediately see that, oh, this set does exactly what we want it to. But yeah, that's all that we need to do for this exercise, and so we are done.